Welcome back everybody, Mr. Allen here. I received a question about the Pascal triangles type questions, and I'm using Pascal's triangle in quotes here. You can't see that, of course, but I am. Just wanted to sort of clarify. I thought the easiest way here might be just go through a quick video kind of talking through a couple of the problems. The first thing to note is you don't have to have a good understanding of Pascal's triangle to do these problems. They simply work out to be very similar to the patterns in Pascal's triangles in the sort of the standard form of the question. So what this question is asking me to do is determine the number of paths from this starting point up here to this ending point down here. And the assumption is we'll never backtrack. So basically, if we're kind of we just work our way down through the problem, the number of different ways I can get to this point right here is just one way. I would walk along this road here. The number of ways I can get to this road, to this corner right here is one way, walking along this path. That means there are two different ways to get to this corner here. And then, of course, I can just kind of continue that and work my way through the problem. The number of different ways I can get to this spot is just one. I'll walk straight down this way here. The number of ways I can get to this then ends up being three. I can take this path, or this path. And what you can hopefully start to see is that the value on each of the corners ends up being the two previous corners, the two corners that lead to it, added together. And so again, continue across. I've got one here, I've got one here. To this corner here, I have four ways. I have the three paths that lead me here, and then I come across, or the one path that leads me down this way. Eventually, I would find that sort of if I continue here, these two, sort of there's one way to get here, this and this is a 3, and then to this corner is a 6. I have the various paths that go through this, sort of the three paths that go through this point, the three paths that go through this point, combined for a total of 6 at that point. And as I sort of see that develop, I know that this will be a 10 and so on. So I'm just kind of working each corner out by adding the two previous corners to get its value. One way to get here, this 1 and this 3 give me 4 paths to this point, this 4 and this 6 give me 10 paths to this point, 20 paths to this point, and so on. Work the whole thing out, find the final value down here. The only difference in this question, we'll start exactly the same way. We're starting up here. We're looking to get down here. You have to recognize that when there's a missing path, of course, we can't take that path. So one way to get here, one way to get here, one way to get here. I suppose using a different color would have made sense on these. Let's just switch it now, I guess. One way to get here. Oh, I didn't switch it. These two give me a 2 here. This 2 and this 1 gives me a 3 here. But because I can't go across, of course, it's going to not allow me to get this combination to add together here. The only way I'm going to get to this point is the one path through here and then down. I can also extend that one path to here, of course, and I'll have another 2 over here. And so this question becomes the same with the obvious logic of if there's no path there, I don't want to combine those values as a way to get to this point. Very similar is the last question here. This is my starting point, and I'm trying to get to the end of the checkerboard. If we know how checkers are played, checkers can only move diagonally, quote unquote, forward. So from here, I could go to this spot. I can go to this spot. There's one way to each of those corners. There are 2 ways then that would allow me to get here. I can go here, I can go here. From here I could go to this spot, and that means there would be 3 ways to get here. From this spot I can go here, which means that there would be 3 ways to get to there, 1 way to get to there, 1 way to get to there, and so on. And you recognize that none of these spots are reachable by playing checkers normally. So full solutions are posted on the website. These are them. And you can sort of, after going through it, verify that you have the right values along the way. The relation to Pascal's triangle is sort of mentioned briefly here. The idea being that the triangle would actually be kind of on the diagonal here. This is row 1 of the triangle, row 2 of the triangle. Eventually this would be row 9 of the triangle. and it would be the fourth position in. So it's 9 choose 4 that gets me this value of 126. Again, not really important, just sort of understanding that that's kind of why we refer to it as Pascal's triangle type problems. This is certainly far more important to be able to just sort of figure along the way and understand that you're looking for paths that exist in order to solve these.